Let's take a look at conservation of energy from a math point of view. Energy is conserved when there's no friction in the process. We cannot have non-conservative forces acting on our object and have energy conserved. Energy conservation problems involve one of two things. In the first case, you have a height change. This could be your typical roller coaster type problem, where you have something that is moving from a high place to a low place, or a low place to a high place. The second one would involve a spring. If a spring is mentioned in the problem, I guarantee conservation of energy is an approach you could take to doing that problem. Now, you could also have problems with springs and height changes. For instance, if we had a spring and we put a mass on it and we compressed the spring and then we shot this mass up a hill, we would see that energy, as long as there was no friction, I should say, we would see that energy is conserved. Now, when energy is conserved, it means to say that the total energy at any given point is a constant. So for instance, if I have a roller coaster and I have this roller coaster car in several different places, I'll call this place 1, 2, 3, 4, the total sum of the kinetic energy plus the potential energy at all of these places is equal to the same value. Now, the way we set these problems up is we look at, say for instance, let's say we have a roller coaster and it's got a certain height of the hill. I'll call this H1. We could compare that to say what's going on when that roller coaster reaches the bottom here. And I will say that H2 is 0. We'll call that the bottom there. I think the easiest way to do these is to draw a picture and label every point that you're interested in with an expression for kinetic and potential energy. For instance, kinetic energy at the top is going to be 1/2 mv1 squared. And the potential energy is going to be mgh1. Down here in position 3, the kinetic energy is going to be 1/2 mv3 squared, and the potential energy is mgh3. What this means to say that that total sum of kinetic energy and potential energy is a constant is to say that the total amount of kinetic energy and potential energy at the top, which I can write as 1/2 mv1 squared plus mgh1, equals the total amount at the bottom, which I can write as 1/2 mv3 squared plus mgh3. And at this point, if you have a bunch of numbers, you can put the numbers in. One of the things you might notice here is that mass is in every single expression, and it will cancel out. Also, in the case that I've illustrated here, H3 is equal to 0, so this whole term goes away. And what we're left with is that 1/2 v1 squared plus gh1 equals 1/2 v3 squared. And depending on how the question is worded, they could give you the height at the beginning and ask you to how fast is it going at the bottom, which would work if we knew also the speed at the beginning. You could be given the speed at the bottom, the speed at the top, and be asked to solve for the height. It doesn't really matter, but this is how you set up the expressions. There's not one equation that fits all situations, but you can create an equation for any situation that exists. We could also do this for position 2. And I think you could see that in position 2, we would have a little bit less potential energy than we did at position 1, but we would have more kinetic energy. The essence of conservation of energy is converting either from potential energy into kinetic energy, or from kinetic energy into potential energy. And that's how all these work. Another example would be when we involve springs. If I take a spring, and let's say I press a mass into it and compress this, I could recognize that when this spring is compressed, and let's say the equilibrium position is over here somewhere, this amount of compression that we have done by delta x is a way of storing energy in the spring. And so I could look at this spring, and let's say I move this mass back into the spring a certain amount of distance and held it at rest. That would mean my potential energy is 1/2 k delta x squared, and my kinetic energy, if I'm holding it at rest, is equal to 0. Now let's say I let it go, and this thing fires off and it's racing along. Now what would be important here is you would have to know whether or not this is a frictionless surface. If it's a frictionless surface, then energy is conserved. If friction is involved, you have to use the work energy theorem. But I'm going to say that this is a frictionless surface, and what I would do is I would look over here and I would say, well, what about the potential energy? The fact is it's not touching the spring anymore. Once the spring is released, there is no energy stored in the spring anymore. But the kinetic energy, because it is moving, will be 1/2 mv squared. And since the total energy, this plus this, must equal the total energy in the second spot, I can just write an expression, 1/2 k delta x equals 1/2 mv squared. You could solve for whatever variable you needed to. We can combine these things. We could, again, have a situation where there was a spring that fires something up a hill. And so let's say we have a potential energy of 1/2 k delta x squared when it's in its loaded position, if that's what you want to call it. The kinetic energy here is equal to 0. But we are going up a hill, so now we're dealing not only with kinetic and spring potential, but we're dealing with gravitational potential. At the bottom here, the gravitational potential energy is also equal to 0, and I'll call this SPE or something, just so we know that we're talking about two different potential energies. Now, maybe the question is, how high would this go up the hill? Once we reach the highest place that we're going to get to on this, first of all, our spring potential is 0. The kinetic energy is also 0, because once we reach our highest point, our speed is 0. But we are going to have gravitational potential energy, and it will be mgh. And again, I can set those equal to each other, because the total in one spot has to equal the total in another spot. And you get something along these lines. What I don't want you guys to do is write down all these equations. What I want you to do is learn this process of analyzing the situation and determining what kinds of energy you have in what spots, and acting accordingly. Now, one of the things that will come up is a pendulum. In a pendulum, we take an object and we raise it up to some height, and I'm going to draw another version of this where it's down at the bottom. That's where it's going to wind up. And the height that we've raised this thing to is the difference in height between here and here. And when we raise it up to that height, we've given it some potential energy. And if I haven't let go yet, my kinetic energy is equal to 0. Now when this swings down to the bottom position, I can say that the gravitational potential energy is equal to 0 because it's at the bottom, but the kinetic energy will now be equal to 1/2 mv squared. And you're going to get a familiar equation that happens when you go from all potential to all kinetic, or all kinetic to all potential, which looks like this. And once again, you'll see that the masses don't matter. Now what makes this tricky is quite often in a pendulum, instead of talking about the height you raise it to, you might talk about the angle that you raise it to and the length of the pendulum. In order to come up with the height using that, we're going to have to do a little bit of geometry. The length of that string in this position is the same as the length in the string when it's at the bottom. What I think you can see is that the length in this position here is a combination of the height from here to here and the length of this side of the triangle. So I can write an expression using a little bit of trig that will allow me to come up with a formula for the height based on the length and the angle. So this side of the triangle is the adjacent side to the angle, so that means that it is equal to L times the cosine of the angle. That red segment and this green segment, when you add them together, are equal to the entire length of the string. Hopefully you can see that there. Those two segments add up to that one. And so the length L cosine theta, which is the red segment, plus H, which is the green segment, equals the blue segment, which is the length of the string. If I solve this for H, I get that H is equal to L minus L cosine of theta, which becomes L times 1 minus the cosine of theta. This guy will come in handy when you do anything that looks like a pendulum. There's a problem in your worksheet about Tarzan. Comes in handy there too.